Hey there, guys. Thanks for joining us. Today we have Arno Puder here. He is a professor at SU. Today he's going to talk about cross-compiling bytecode. He is the creator of a language called XMLVM. And today he's going to talk about cross-compiling code for the iPhone. So here he is.
Thanks, Ben, for the introduction. And well, thank you very much for inviting me out here to this Google Tech Talk. It's actually my second Google Tech Talk here, so it's nice to be back again in Building 42. And today I wanted to talk about, as Ben already mentioned, about my latest project, cross-compiling Java applications for the iPhone. And it's kind of a project that is part of a bigger project that I call XMLVM, and I will talk about a bit more about that during my presentation. But you know, when the iPhone is a very hip device nowadays, and you see many people having an iPhone. Now, unfortunately, Apple is very restrictive when it comes to opening up their hardware. They create such beautiful tools and products, but then they're very restrictive when it comes to opening up. As a matter of fact, I'm not even quite sure if I had used the official SDK for doing my work, I probably would not even be allowed to stand here in front of you to give this presentation. So fortunately, I've only used open source tools, of course also using a jailbroken device, so I can talk in public about what I've done. For today, the agenda is I will tell you a little bit about Objective-C. Objective-C is the language of choice from Apple, not much used outside of Apple. But since not many people have seen it before, I have a few slides to give you at least a quick introduction on Objective-C. And then basically, I talk about how we cross-compile Java to Objective-C to create native iPhone applications. And I have a bunch of demos throughout, so I hope that you can also see some of the code that we've been working on in action, in fact. OK, the quick rundown of history of Objective-C. So it was designed in the early 80s by a guy called Brad Cox. And Objective-C is just like C++, an object-oriented extension to C, just like C++. Except that they've taken more inspiration from Smalltalk. So it's a dynamic language, and you will see shortly on how that works. In the late 80s, there was a company called Next Software that licensed Objective-C, and they used that language to develop a user interface called NextStep. And around that time also, I believe Steve Jobs, well, he left Apple for some time, and he joined this company, Next Software, and also got exposed to Objective-C during that time. And when he returned to Apple, I think it was the reason that he brought then NextStep and also Objective-C over to Apple. But anyway, so in my little timeline slide here, you can see that then in '92, the Free Software Foundation added Objective-C support to their GCC compiler suite. Then in '94, it's being standardized by Sun Microsystems and next to something called OpenStep. I do know that GNU also has an implementation of NextStep they call GNU-Step. Well, and then in '96, Apple acquires Next Software, and since on, Objective-C is heavily used inside of Apple. So Mac OS X is based on Objective-C, and OpenStep is now called Cocoa. So it's the GUI library used for developing Mac applications and also used to develop iPhone applications. OK, let me give you now with a little quick rundown here. Let me show you some code, Objective-C code, so you have a better idea on what it feels like actually to write an Objective-C application. So in Objective-C, you have a strict separation between interface and implementation. And on this slide here, you see an interface definition of Objective-C. And you can see there's an interface called fraction, and it inherits from a base class or base interface called NSObject. Now, NS, you can already tell by this prefix, stands for next step. So even though we're now talking about modern iPhone applications here, or Objective-C, the base class libraries still has these classes that came from the original Next Computer company. But you see there are two members for a fraction, numerator and denominator, and there are some instant methods here. And you can see instant methods are prefixed by a minus sign. So whenever you see this minus sign, that tells you that you actually have an instant method. The return type is in round brackets, and while the signature is a little bit different from what you're used to from C++ and Java, basically they call it a selector. So if you take something like set numerator, that is actually called a selector. And then the actual parameters, or the formal parameters, are mentioned again after the selector. So you can see kind of if you have done any kind of programming, I'm sure that you can immediately understand how to read this. Okay, once you have this interface definition, you have to implement it. So you have to provide an implementation. So on this slide here, you see how to implement that. So there's a new keyword now called ampersand implementation. And here's how you implement class fraction. And well, you provide the implementation in curly brackets, no big surprise here. And you can also see by the implementation of method print that you have full access to the C runtime library. So we just use printf to print out the fraction. And the other methods here for accessing and reading the members are just as you would expect it from any language. So then once you have created this class called fraction, and here's how you can use it. So the main entry point of an Objective-C program is, again, the main function, just as it is as for C and C++. And I guess the first thing that looks a little bit strange now is the square bracket here on the first line of code. And what happens here is basically you have fraction as the name of the class, and you send it the method called alloc. So basically, those square brackets denote sending a message to an object. So what happens here is, in this first line, that you send fraction, the alloc method, and that would correspond to allocating memory for class fraction. And then what you get returned is a pointer to this new object, and then init would be the constructor. So you do alloc to allocate memory, and then init to actually initialize the object. And then you can see how to use the selectors that I've defined for class fraction by setting numerator and denominator, and I can print it. So basically, that kind of is a little bit different syntax, but I think you can immediately see how this works. On the bottom, you see how to release an object. So there is a method called, or a message called release you can send to an object that will basically deallocate the object. If you have multiple parameters, and here is a bit of a departure from other languages. I mentioned already before, they don't really call it a method name, they call it a selector. And a selector determines method dispatch, so that determines which implementation you're invoking. And if you have multiple parameters, so for example, if in my class fraction, I wanted to have a method that sets numerator and denominator at the same time, then here's how you would do in Objective-C. And I think the intention of Objective-C was that they were trying to create some kind of readable interfaces. So if you just look at the bottom of this slide here, so I have this object frag, and I send it, I say set numerator 1 and denominator 5. So even like in choosing the selector, you can almost read it like an English sentence. So you say I have a fraction here, and I set the numerator and denominator. And so that basically is a little bit of a departure from just the method name and the list of formal argument types that you have in other languages. Now, I should also mention here that overloading is not allowed for selectors. So if you have two selectors, identical selectors, that only differ in the formal argument type, that is not permitted in Objective-C. So which, of course, has some repercussion when you try to cross-compile from Java to Objective-C, because you do have overloading based on formal argument types. And I'll talk about that a little bit later. Let me talk a bit about garbage collection, because just like C++, Objective-C does not have a garbage collector. It relies on reference counting. So if you implement your own class if you derive from your own class from NSObject, you inherit some basic reference counting functionality. So what you can see here is, again, I initialize or I create a new object, I initialize it, and then there are three messages three messages you can send this object. There's one message called retain count, and that just returns the current reference count for that object. So after you immediately create the object, the reference count would be 1. And you can send an object the retain message, and that would just simply increase the reference count by 1. So you can see how the reference count will just be bumped up twice here by sending the retain message twice. And then release just decreases the reference count. And once the reference count drops down to 0, then of course the object is going to be deallocated. So now it's your responsibility as a programmer to call these retain and release messages. Now, I heard that, that Apple is planning on doing a new version of Objective-C where they actually integrate a garbage collector into Objective-C, but that is still on their roadmap. So as for now, if you want to write an Objective-C application, you will have to do your own cleanup after yourself. There is one thing that they have added to the runtime library that makes it a little bit easier for garbage collection. So on this slide here, I explained to you a thing called the Autorelease Pool. So the Autorelease Pool is just a class that can do a little bit of, while managing a bulk of objects. So basically what happens is if you create an Autorelease Pool, any object that is being sent the auto-release message will be added to that auto-release pool. So if you look at the code on the bottom here, so first of all, in the first line of code, I do create a new auto-release pool. And you can see just like an instance of a class called NS auto-release pool. Now then here, the next thing is I again create an instance of class fraction. Now notice that I not only call alloc and init, but also I send it yet another message called autorelease. That's a message that is also inherited from the base class NS object. But by invoking autorelease, what will happen is that this fraction is going to be added to the autorelease pool. Now, when the release pool itself is released, so on the last line of this code sample here, you see that, that I'm actually releasing the auto-release pool. Then the auto-release pool, as part of its cleaning up process, will release all the objects that it has accumulated over its lifetime. So basically, by releasing the auto-release pool, as I'm indicated on this comment here, you will also automatically delete that frac instance. More precisely, what happens is here that the auto-release pool is decrementing the reference count by 1. So of course, the auto-release pool in that example only deletes the frac instance because the retain count is equal to 1 for this example here. Now, Cocoa, as the GUI library for Apple, is making heavy use of the auto-release pool. So if you create like widgets in the Cocoa library, then they automatically added to the current auto-release pool. You can also nest auto-release pools. You can have like an auto-release pool inside an auto-release pool. So that's also possible. So one more thing that you have in Objective-C, and that's kind of a radical departure from C++ and Java and is more in tune with what you had in Smalltalk, the dynamic invocations. So basically, you can send any object, any method, and the compiler will just simply take it. So here I have an object like a variable OBJ object, and I send it some method. And the compiler may say, well, you know what, I don't really see that method in your inheritance hierarchy, but I just trust that you know what you're doing here. So if the object should not implement this method, some method, then it would cause a runtime exception. But the nice thing is that you don't have to have like a strict inheritance relationship. So the bad thing is you have no strong static runtime, compile time type checking, but the good thing is that you have a very flexible dynamic invocation scheme here. And that is also heavily used for the Cocoa library. For example, there is a widget called UI table that implements a little table widget for the iPhone, and the way they connect to a data source. So a data source just has to implement a few methods, but you do not have to derive your data source from an interface. Okay, so much for Objective-C. So now I want to jump into how actually to develop a little iPhone application. And here on this slide, you see the infamous Hello World application for the iPhone. And of course, since it's for the iPhone, what you see on this slide is, of course, Objective-C code making use of the Cocoa library. And if I just quickly walk through this piece of code here, so of course you first have to define an interface. And your interface, if you want to write for the iPhone, you have to derive it from something called UI application. And you have to overload a method called application.finish launching. So of course, there's nothing that I came up with. That's a method that came from the Cocoa library, comes from the Cocoa library. So that is basically your main entry point. So once the application has finished loading, well, that is then what the iPhone will call in order to launch your application. Now, in the implementation, you see what the application is doing here. So basically, what happens in the first line here is you use class UI hardware to retrieve the full screen coordinates of the iPhone. So that basically would give you something called a CGRect that gives you the full screen resolution of the iPhone. And then the next line, you instantiate something called a UI window, basically giving it the full size of your screen. So UI window, if you have done any swing coding, would somewhat correspond to a JFrame. So here you basically just create the basic container for adding your own widgets. Then you do some things like you put it to the front and you set it to visible. The next big thing that happens in this code here, you instantiate a class called UIView. And that would correspond roughly to a JPanel if you're familiar with swing programming. And again, you give the UI view the complete size of the full screen resolution of the iPhone. And then you see then one line saying Windows set content view. It's where you add the view to a window. So that's the same thing what you do also in Swing. You just say JFrame add a JPanel. The next thing that happens here is you instantiate a UI text label. And well, that very roughly corresponds to a J label. It's just basically a text label, although you can do much more in the Cocoa library. And you can see that you set the text by saying hello world. And then you add the text label over to the UI view. And that's it. And that would just pop open a window and horizontally aligned, say, hello world on the iPhone. Okay, so what is on this slide, again, is the Objective-C version of that. Now, remember what we're trying to do. We're trying to allow developers to write an iPhone application using Java. So the first thing that we have to do is we have to kind of map the API that is defined by Cocoa over to Java. So which means all these base classes that you see on the slide here, UI application, UI view, UI window, we have to create some kind of corresponding classes in the Java world. So the first thing that we did is actually to do that. And what I show you on the next slide here is now hello world in Java. And you see it follows exactly the flow that you saw for the Objective-C version, except now we're using Java. And of course, now I have to create some Java classes that implement UI application and UI hardware. So actually what, for the first demo, and that's kind of like the little teaser, but I have a bit more fun demo at the end of this presentation. I want to show you how actually this Hello World runs on the iPhone. It's not a big show-off, but again, something more impressive is coming up shortly. And basically what I'm going to show you here is, while we have this Hello World application, and I have not yet told you how we do cross-compilation, but just believe me for now that we can cross-compile this Hello World over to Objective-C. Now, if we use the Objective-C compiler, then you just link it with the native Cocoa library to create a native iPhone application. You can run that on the iPhone. Now, what you can also do is, of course, now you've seen this Java class called UI application. So how about now actually creating a Java implementation of this UI application, for example, based on Swing? which means now that I could run my Java-based iPhone application as a pure Java application on my desktop. Okay, and that's going to be the first demo I'm going to show you. So I switch over to Eclipse. And here in this window, you see actually you see this Hello World application I've had on the slide. And you can see I have this UI text label here, and if I click on that and if I open this class, you can actually see there's an implementation that goes along with it here. And if you go a little bit down here, there's a method called drawRect, and that is just using Java 2D to actually do this rendering of this UI label. So what I can do is I can actually run this application here as a pure Java application, and when I do that, well, I added a little bit of eye candy here. So you have, I put a little chassis snapshot in the background, but basically that's how it would look like as a pure Java application running on a desktop. Now I have an iPod Touch up here, so I can now run the cross-compiled version, and of course that just does the same thing here, so it looks exactly the same as the Java version. So that's not much of a show-off, and like I said, I promise you a somewhat more interesting demo, and you can already see there's some scroll bars here called accelerometers, so that will give you some indication on what's coming up here. But let me go back to my presentation here, and as the next thing, explain to you how we actually do the cross-compilation, and that basically comes closer to the XMLVM project where we got this name from. Before I do that, I just want to point out some of the challenges when cross-compiling Objective-C to Java. I already mentioned a few things, but just kind of to reiterate and also to refine some of these points. Well, Objective-C has no namespace support. So you have everything in the global namespace. I mean, of course, there's a namespace introduced by class definitions, but there's no package thing. There's no way of defining modules in Objective-C. Also, I mentioned there is no method overloading. So you cannot have like two methods have the same selector, but only differ in their formal argument types. Not possible in Objective-C. Now, if you have a Java program that is doing that, then, I guess at least how we do it, we use name mangling. So we just append the signature to the method name, and then we avoid these problems. There's no garbage collection. So Java has garbage collector, Objective-C does not. So of course we have to deal with that somehow. We do make use of reference counting, but that also means, of course, we cannot do certain things or we cannot reclaim certain kinds of data structure. If you have a cyclic data structure, we would not be able to clean that up. Also very interesting, Objective-C has no static member variables, so we have no choice but to create global variables. Kind of like a very awkward thing, but that's just the way things are in Objective-C. So again, you have to be very careful by using name mangling of not to have any collisions. So these are the challenges that you have on the language side when you talk about cross-compilation. You also have some challenges from the Cocoa side, from the GUI library. And if you look a little bit closer at Apple's API, they make use of C functions. So they are like, there's a function, for example, called CGColorCreate. That's a C function. It's not like what you should have if you do a proper design, object-oriented design. It's not like a static member of a class. No, it's actually a C function. Now, so of course, you have to think of how can you map that API over to the Java world where there is no function. There's at best a static member, a static method, but not a function. Objective-C has value types. So in C++, struct and class are almost identical except for the default visibility of its members. In Objective-C, a struct is actually a value type. So when you pass a struct around, it actually does a deep copy of all its members. And it's also being used in Cocoa. For example, the CGRect I mentioned before, I had on the Hello World program. That actually is a struct, so which means it does not do copying of references to pass it around, but it actually is copying that whole struct. So you have to be very careful when you pass these values around, because then you have different semantics with call by value, call by reference. It also uses like this old C programming trick of using pointers to add additional output parameters. So basically, if you've ever done any systems programming, you have a pointer to something, and you use that to pointer to a pointer to add additional output parameters. So they also do that in Cocoa. And since we don't have that in Java, of course, we have to be a little bit creative on that. And last but not least, they're using delegation here, making use of this dynamic invocation. Already pointed out this UI table where a data source just simply has to implement certain methods, but does not have to be derived from an interface. So that, again, we can only very, with big problems, mimic in Java. So let me start talking about the cross-compilation, because that's, I think, the most interesting part of this project. And like I already mentioned, there's an umbrella project called XMLVM that we use for doing very flexible manipulations on a bytecode level. And just to mention it up front, we do not cross-compile on a source code level. So we do not take Java source code, but actually what we do is we take a class file as the first input to our toolchain. So on the next few slides, I give you a little demo here, by basically walking you through that. So I'm going to make use of this class here. So take a very close look at this class, because I'm going to kind of single step on bytecode level through this class here. So just take a quick look at this here. So you have a Java class called Calc. It has one member called x of type int. And you have one method add with one formal parameter y. And all that happens in the implementation, we add the parameter to x. So x plus equals y. Not a very exciting class, but it's just enough to just explain to you how we do the cross-compilation. Now, our toolchain, the first thing it does is it takes the class file of this class here. So first you run it through a regular Java compiler. So take Eclipse compiler, take the Sans JDK compiler, and you end up with a class file. Now that is the thing that we feed into our toolchain. And the first thing we do is we create an XML document out of it. It may sound a little bit awkward, but you will see shortly then what we do with that XML document. And it also is where this project gets its name from. So XMLVM, XML, well, that's obvious, and VM, virtual machine. So on the next slide, I'm going to show you what this XML document looks like for this class Calc. And that's a lot of ugly XML code. Now, once again, as a reminder, this XML that you see here has the same information as the binary class file. So there's a bidirectional mapping between a class file and this XML document. So I can also take this XML document and map it back to a binary class file. So all the information you find in a class file created by a Java compiler, you will find in this XML document. It always begins with the root node XMLVM. That's the name of the project. And then on the next level, you have a class tag that defines a new class. And you can see, well, there's the name of the class. And the children of class define this class. So you have an XML tag called field that defines the member x of type int. And then you have this method add. You see mentioning of stack and local. So basically, how much stack space does this method need? How many local variables does this method need? The method has a signature. So it has a return type void. It has one formal parameter of type int. And then I guess the meat of this XML document would then be the code tag. And that contains actually the bytecode instructions that you would find in a class file. And that is what the Java virtual machine would execute step by step in running this class here. So what I want to do on the next few slides, actually, since that's something that most people have not really seen, like what really happens inside a Java virtual machine, I want to single step through this piece of code here. So actually, I'm going to zoom into this code segment here. And I'm just going to single step through each of these bytecode instructions. You have a better idea actually on what happens inside the Java virtual machine. So the setup for this example is here that, I have an object that has a member x, and I assume that it's initialized with 11. So this one object instance I'm looking at, its member x is initialized with 11. And these two local variables, you can access them through an array. So locals index 0 is always this pointer, so pointing to the object itself. And then starting from locals index 1 to locals index n are the arguments that are being passed to the method. Now, since my little add example here has only one input argument, there is only locals index 1 that corresponds to the actual parameter. So that's the initial setup. So the first bytecode instruction that will be executed of this method is the load instruction. And what load is doing, it is pushing the locals index 0 onto the stack. So at this point, I should mention that the Java virtual machine is a stack-based machine. So everything is done over a stack. And that's similar to the way also .NET has defined its virtual machine. So by executing the first bytecode instruction, what would happen is that locals index 0 will be pushed onto the stack. Now, I'm an old-fashioned guy. I still did a lot of assembly, so my stack grows from top to bottom, just to mention that. Sometimes my students get a little bit confused because they kind of think stack should grow from bottom up, but I'll do it the other way around. So the next instruction is called dub, which is a short form for duplicate. Well, that just simply duplicates the top of the stack. So we have now this on the stack, and now after executing that, we have now this twice on the stack, pushed a second time. The next instruction is called getField. And you can just look at by the XML that we're trying to read a member from an object. And you can see, well, we're trying to read member X of a class Calc. Well, that tells the virtual machine what member to read. But of course, what getField needs to know from which object it's supposed to read this member X. Since, of course, we can have multiple instances of class Calc. And getField gets that information from the stack. So what getField is going to do, it is going to pop off the top of the stack, is going to use that pointer to address the object, is going to read the content of variable x, member x, and it will push that content of variable x onto the stack. So with the next instruction, getField, it will pop off this, and it will push 11, which is the current value of x. Then we have another load instruction. So load index 1, well, that will push locals index 1 onto the stack. And that is now the actual parameter. So that is what we are passing to the method. And so now we will just push 31 onto the stack. So now we actually have the maximum stack size that we need for this particular method here. The next instruction is called iadd. Well, integer add, well, that just adds to integers. And since we're talking about a stack-based machine, what does it do? Well, it just pops up the last two integers, computes the sum, and then pushes the sum back onto the stack. So 11 plus 31 is 42. So you can see I'm big fan of, well, OK, you guys know what I'm talking about, right? 42. So the next instruction, putField, is then the reverse of getField. So it actually writes now a value back to a member. So again, you can see putField again says, well, I want to write back to member X of class Calc. Now, what does putField need in terms of parameters? Well, it needs, first of all, just like getField, it needs to know to which object. So it needs a pointer, it needs a reference to the object. And of course, it needs to know the value that's supposed to be written back. Well, and guess what? Exactly those two things are right now on the top of the stack. So putField is going to pop off two elements of the stack. And it will then use this pointer to access the object, and it will write 42 back to x. So now in the next instruction, you will see that x now will become 42. And that, of course, return is then going to leave the scope of this method. But that basically shows, gives you a rough idea on what happens inside the Java virtual machine. But just, again, to point out that the Java virtual machine is a stack-based machine. So everything happens over a stack. That makes the instructions very, very simple. So it's just a matter of pushing and popping some data off the stack. Okay, so that's all good and fine. So I've explained to you in great detail on what this XMLVM looks like. Now, but how do we go from here to Objective-C? And well, actually what we do is, and that may look a little bit awkward, we're making use of XSL style sheets. So since now we have this bytecode program represented through an XML document, we actually have written a style sheet that now cross-compiles or generates, based on this XML document, Objective-C source code. And we do that by just simply mimicking the stack machine in the target language, which in our case now is Objective-C. Now, if you look on this little code sample on the bottom here, and let me first direct your attention to this XSL template on the bottom. So you see there's an XSL template match IAdd. So this style sheet, this particular template, is going to fire whenever it comes across the IAdd instruction in my XMLVM document. Now, whenever I see the IAdd instruction, it is going just simply to spit out the code that you see in black here. Now, the code in black is Objective-C source code. And if you take a close look at what this code is doing, it actually just implements the behavior, the semantics of the IAdd instruction. So you see I have some helper variables. I have a variable called _stack that just represents my runtime stack. I have a variable called _sp for stack pointer. I'm using a pre-decrement to mimic a pop. I use a post-increment to mimic a push. So what these 3 lines of Objective-C code are doing is just exactly what would happen in the Java virtual machine. It pops off 2 integers and pushes the sum back onto the stack. Now, those variables op1, op2, and stack are based on a type def that you can see a little bit above this code segment here. So it's a union, basically, that is a union of all the primitive types that are supported by Objective-C. So I can have type safe access to whatever data type I have on the top of the stack. Now, of course, I am relying on the fact that Java-C, the Java compiler, is producing correct code. So when I know that when I execute the IAdd instruction, I know there are 2 integers on the stack. So I know that I can access the top of the stack using the .i member of this union here. Now, what I show you on the following slide, I show you actually what this class Calc looks like completely cross-compiled to Objective-C. So, well, that's a lot more code than my original one-liner here, x plus equals y. But basically that, the code you see on the slide here, first of all, is Objective-C code. And you can see on the right-hand side, I have these curly brackets here that show you the respective code, what kind of bytecode instruction they implement. So somewhere on the bottom you see IAdd. So you can see those 3 lines of code that I just explained to you on the previous slide. But you can see those are this handful of bytecode instructions that I just single-stepped through. And you can see like how every of these bytecode instructions just results in very, very simple piece of code that just does a little bit of stack manipulation. So you can see how the dup thing is just simply taking the top of the stack and just pushing it one more time. Now, of course, there's a bit of boilerplate code that we have to create. For example, these helper variables, stack and stack pointer and op1, op2. So those are created by the style sheet for the method tag. If you remember from XMLVM, there's an XML tag called method. So the style sheet for that XML tag would emit the boilerplate code to initialize these helper variables. A few more things I want to point out here. So you can see the method add. We use name mangling here. So we name mangle the formal argument types into the method name in order to avoid this method overloading problem that we don't have in Objective-C. And one more thing I also want to point out here is you can see that the way we do garbage collection is that at the entrance of every method, we create an auto-release pool that we release upon exiting the method. Now, of course, that's just a crude approach here. So if you have like a very lightweight little method, of course, creating an auto-release pool is kind of overweight, is kind of overshooting. Likewise, if you have like a big for loop that just simply creates objects before you exit the method, of course, you would also accumulate a lot of garbage that would take a long time to clean up. But that, at least, that's the first approach to garbage collection. We use reference counting, and every method gets its own auto-release pool. So whatever objects are created inside that method, as long as their retain count is larger than 1, the moment you exit the method, that is the time when the objects would be reclaimed. Okay, I think it's time for some a little bit more cooler demo here. So let me show you a little bit more complicated application. And in the XMLVM project, it's become kind of customary to do a little application we call Fireworks. And this application is just implementing a little fireworks thing here, and you can see what it does. It just simply lets these sparks fly. Now that is, of course, a little bit more complicated than Hello World. So that is using a lot more of the Cocoa library. We're loading images here. We do animation. We have timers. We move things around on the screen. But what you see right now is, again, the 100% Java applications. For all these Cocoa classes that I'm using here, I've actually implemented a Java version. So I can run this as a pure Java application. So we're making use of Java 2D to do all this animation. So that is the application that we have. Now, this application can be cross-compiled, and if I run it now on my iPod Touch here, of course, you see the same thing here. So it's exactly the same application. I did not have to change one line of source code to make it run here on the iPod Touch. Now, the iPod Touch has special hardware. Just like the iPhone, it has a thing called the accelerometer, which means that you can sense change of orientation. So the way the application is written is that the sparks always follow gravity. So if I turn my iPod Touch around, you will see that the sparks follow gravity and always go to the bottom. And well, how can I mimic that in my little Java emulator? Well, I can use, that's what I have these scroll bars for. So if I use my mouse here to use these scroll bars, I can also change the orientation. So by pushing Y down here, I can make the sparks go fly up here. If I go with X here, I can make them go to the northeast corner of the display. So that's kind of like, with the accelerometer, you can just do 3 scroll bars for the 3 axes. So that's kind of like a little trick. Now, the iPhone also has more advanced things. It has a multi-touch interface. So probably all have seen this famous pinch for zooming in. So you take 2 fingers and you push them apart to zoom into, for example, Google Maps that is running on the iPhone. Now, on my laptop here, I only have 1 mouse. So how can I simulate that piece of hardware, this multi-touch interface, if I only have 1 mouse? Well, what we have decided to do is, we realized that we actually, why don't we use the iPod Touch here as a remote control? I mean, I have a multi-touch interface on the iPod Touch here. So what we have done is we have created a little application that runs on the iPod Touch that just simply transmits the information of the accelerometer over to my simulator. So let me call this application now. Typing in the IP address, turn on. Okay. So actually what happens now is I run this application. There's nothing you can see on the application on the iPod Touch, but observe the scroll bars of my simulator. When I turn my iPod Touch here, it's kind of by magic almost, it's changing the orientation of the scroll bars. Okay, so and also then, of course, as a consequence, is changing the orientation of where the sparks fly. Okay, that's what I wanted to show you. So sorry for the little glitch here. Now, this application I just showed you that I used as a remote control, we have also created using the same technology. So this application I just showed you, we have written as a Java application and cross-compiled it over to the iPhone. So what I can do now is I can actually launch this application in a second simulator. So let me do that now. So this is the application I was just using to type in the IP address. So now I have two simulators open. Let me just, oops, sorry. Let me move this down here. And what I'll do now is I just type in the IP address, which of course is localhost here on my laptop. I turn on the on switch. And now if I use the scroll bars here in the second simulator, of course it is going to control then the first simulator. So you can see that we already have actually pushed our little Java Cocoa library to some extent here. So you can see there are some user interface elements that we already implemented here. That makes the iPhone so famous, like all these little cool sliders and tables and preferences settings and so forth. So we even spent some time to do like the same color gradient, to make it a little bit look like you actually would expect it from the iPhone. But basically, that's a little bit more complicated application because also is using remote communication. So it also is actually doing HTTP request to upload the sensor data to the second simulator. So that's actually a lot more complicated than the fireworks application here. Well, that's the demo. Let me run through a couple more slides to wrap up here. So XMLVM is an umbrella project, as I mentioned, for bytecode manipulation. And on this slide here, I just show you some of the other things that we have done as part of this project. And what you see on the top here are the different bytecodes we can feed into XMLVM. So I've shown you here Java bytecode instructions. That was the whole demo I was showing you here. But we can actually also feed .NET bytecode into XMLVM. So you can take a .NET executable, and you can also create this XML file out of it. And as of recently, we also support the Ruby virtual machine. Ruby 1.9 has its own virtual machine. They have this funny name, YARF. I don't know. Ruby was done by Japanese guys, so they have like these interesting acronyms. But YARF is the name of the Ruby bytecode, and we can also feed it into XMLVM. Now, on the code generation side, we can create different languages. So first of all, we can map it back to Java bytecode. We can map it back to .NET bytecode. We can map it to JavaScript, to Python, and we can map it to Objective-C and C++. Let me just make a few points here. So one thing we can do is we can take .NET bytecode and we can write out a Java class file. So we have also a bytecode level cross-compilation from .NET bytecode to Java bytecode. Base that with the backend for Objective-C I've just shown you, it would also be possible to write an iPhone application in C#. So if we had the Cocoa library based on a .NET API, you would be able to also write iPhone applications using C#. We can cross-compile from all these bytecodes down to JavaScript. So actually, the earlier Google talk I mentioned that I gave here 2 years ago was actually just focusing on how to cross-compile Java bytecode to JavaScript. So that we use actually for doing Ajax applications. So it's similar to the Google Web Toolkit. So we take Java source code, we compile it to bytecode instructions, and we can create JavaScript out of it. So actually, if you go to our homepage, you will see some demos on what we can do there. We actually have, that reminds me, this fireworks now in JavaScript. So, oops, that is. So here you can see, like, here's an index.html file. So if I double-click on that, it will fire up Firefox here. And what you can see now is actually fireworks running as native JavaScript code inside of Firefox. Now, I've used an animated GIF for the sparks here because it looks a little bit nicer on a big screen here. It's not used the colored sparks I've used for the iPhone version. But that's the same algorithm that has now been cross-compiled over to JavaScript to run as a JavaScript application inside of Firefox. So we use that to develop Ajax applications. By the way, this window, don't be fooled. We're using an Ajax library called Cookstew, and they give you like a desktop look and feel inside the browser here. So this window is actually just a diff. They just do, I can move it around. if I close the tab here in Firefox, you can see that it actually then also closes the application. So there's also a good moment to introduce some other members of my team here. So I have one student who joined me today, Joshua Melkorn. He has done a lot of work on the .NET to Java bytecode cross-compilation. There's another student, Jessica Lee, who also has done some work on that part. Joshua is also going to spend some time for his master's thesis trying to cross-compile Android applications to the iPhone. Since Android is Java-based, we think it's quite possible that you should also be able to cross-compile an Android application over to the iPhone. And there's one colleague of yours, actually, a former student of mine, Sascha Heberling. He's based in Zurich, Switzerland, and he did a lot of work in the early days of XMLVM for this Ajax framework. So he worked a lot on cross-compiling Java to JavaScript. So before I wrap up my presentation, I wanted to just kind of pitch you one more idea. You know, I'm an academic, so I don't do really like products. I do some prototypes and demonstrators, but I try to push the envelope in terms of developing new ideas. And one idea I'm kind of toying with right now is XMLVM. At the moment, as you've seen on the previous slide, has various flavors. So we have XMLVM for Java bytecode instructions. We have one flavor of XMLVM for .NET bytecode instructions, and yet, as of lately, a third version that has Ruby bytecode instructions. But at this point in time, an XMLVM document only contains bytecode instructions of one virtual machine. So either you have an XMLVM document only with Java bytecode, or only .NET bytecode, or only Ruby bytecode. So the use case that I'm working on right now is how about if you take aspect-oriented programming, AOP. In aspect-oriented programming, what you do is you have an aspect you weave into an application. Now, you're all smart Google guys, so I'm sure you're very familiar with that. Aspect-J is like the big AOP framework in Java. Now, how about if you have a C# application and you weave in a Java aspect? So basically, you achieve reuse for aspects on a source code level by being able to leverage your aspects written in Java and weaving them into a C# application. Now, what would happen in that case is that you end up with a version of XMLVM that has not bytecode instructions from one machine, but kind of like an interleaved. So you basically have bytecode instructions from two different virtual machines. Now, the question is, what do you do in that case? I mean, what do you do, for example, if you have an IAD instruction from Java that I've explained to you earlier, and you let it loose on an unsigned data type that is available in .NET, but you don't have in Java. Java doesn't have unsigned ints. I call this the abstract virtual machine. It's kind of like a super virtual machine, and what we would have to do for that is we would have to define the semantics of this virtual machine in order to define these cases. You know, what happens if you mix bytecode instructions from two different virtual machines? But again, the benefit would be then for AOP. I think that would be a very interesting project. So that is the latest thing that we're working on. So to wrap up here, as an outlook, of course, you know, like I mentioned before, we don't do products, we just do prototypes. Now, everything we have done here is available under an open source license. So I mentioned, put the homepage, xmlvm.org, easy to remember. It's hosted on SourceForge, and everything is available under an open source license. Now, there's still lots to do. I mean, just for the iPhone part, I mean, we have implemented some of the Cocoa classes for the user interface elements for Java, but there's still, of course, a lot more. I mean, the iPhone is famous for its user interface elements, and of course, if you want to write Java compatibility classes, you would have to do a lot more work on that. And as I already also mentioned, one thing that Joshua has just begun to work on the Android to iPhone cross-compilation. Well, guys, that wraps up my presentation. I would thank you for your attention, for coming here today. And if you have any questions, I guess I would be happy to answer them now. the mic.
Yeah, this stuff's pretty awesome. Thanks for bringing it in. I was thinking about the Android to iPhone cross compilation during the talk, and it seems like the UI would be somewhat different between the two phones, but it does make a lot of sense if you were coding an app and you wanted to be able to have an iPhone version and an Android version to share some code would be really cool. How close is the library for sort of non-UI elements? Would you be able to share some Java classes that have less dependencies between an iPhone app that you wrote in using XMLVM and an Android app?
Yes, we have, like for the fireworks application, for example, one classic example is we have a random number generator, right, to place these sparks by random on the screen. I mean, there is a class in the Java runtime that implements a random number generator, and of course, if possible, we do leverage functionality we already have in the Java runtime library. Now, when it comes to mobile devices, of course, it does not make any sense to cross-compile a Swing application. I mean, Swing is meant for desktop applications. It would not make any sense to write any compatibility classes for Swing for the iPhone. Now, when it comes to Android, again, we're just beginning with that project, so I cannot talk too much about it, and I'm also waiting for you guys to open source it properly, or I don't know exactly what the status is of that now, but the thing is that Android, the very least I do know, is also targeting mobile devices. So I'm fairly confident, whatever the abstraction is, that we have a better leverage on cross-compiling that to the iPhone than for example, Swing to the iPhone. So to answer your question, yes, we try to leverage as much of the native library if we can to make it easier for the Java developer so they can use what they are used to, data structures, for example, hash maps and so forth. But for the UI elements, we stick with the native API.
Yeah, can you talk a little bit about the performance metrics? Especially I'm interested in Java to JavaScript compiler. And also compare or contrast it with the hand-coded Java to JavaScript compiler in
Compared with what?
Compare it with the hand-coded Java to JavaScript compiler in GWT, or Google Web Toolkit.
Yes, OK. So the question was about the performance of our cross-compilation. I mean, if you remember this piece of code, let me just go back to this one slide here that, I mean, this is a lot of overhead, right? I mean, that is by no means as efficient as this one line x plus equals y of my original Java program. Now, this here is Objective-C, and we're using an Objective-C compiler to compile it down to machine code. Actually, we have observed that the GCC compiler is very smart. It can actually optimize away a lot of this boilerplate code. So if you look at the generated machine code, you wouldn't see the stack anymore. The stack goes away. It's still not quite as efficient as the original Java program, but the native Objective-C compiler can optimize away a lot of this boilerplate code here. So for the Objective-C side, I'm not concerned at all. Now, you also asked about JavaScript, and that's a different thing because JavaScript is an interpreted language, and of course, there we cannot do any kind of optimizations. I mean, JavaScript would look like just as ugly. If I ran this through our JavaScript backend, it would look something similar like this here, of course, then using JavaScript as the target language. Now, that, of course, is a lot more inefficient than a natively written JavaScript application. And of course, I also have to admit that Google's Web Toolkit, since they begin on source code level, they have a source code level cross-compiler, they can do a lot more optimizations. So their code, yes, of course, will be a lot more efficient than our generated code. Okay, yes, the thing is, I'm an academic, I have only very little resources. I have not Google, like you guys have like a whole team of programmers, you can tackle all the Java source code level. But doing that, what GWT people have done is very complicated, a lot of work. Bytecode level is a little bit more simplistic. Now, I've also given you the fireworks demo for JavaScript for a purpose to show you that actually, it runs pretty cool. I mean, that application is a few thousand lines of JavaScript code and very bloated compared to a natively written application if I would do it in native JavaScript. But it still performs quite OK. Now, when you specifically ask for AJAX application, my response to you would be, well, for AJAX, you would not want to do any number crunching applications anyways inside a browser, right? I mean, you do UI applications. And for those, performance is not that big of an issue. So even though I completely agree that the way we create JavaScript code is not as efficient as, for example, Google's Web Toolkit, I think for the kind of application that you would do or that you will do for AJAX, it's perfectly OK. And actually, if you go to the XMLVM homepage, you will see also a little bit more complex application that we have done for AJAX. And it works like a charm. I think there was a question in the front here. Not anymore?
No, I was asking about performance.
OK, another performance questions. Any other questions? Well, then, again, thank you again for your attention. Now, just to come back to my little thing here that as an academic, I have only very few resources to my disposal. I know you guys have your 20% project, so maybe you might want to consider using one of those ideas I've pitched you today as your 20% project. So, talk to me if you're interested in that. Anyways, thanks for coming today.